Right, thank you. So thanks everyone for this excellent meeting and the organizers for the invitation. I want to talk today about 3D simulations of planet formation by vortex trapping. So I would like to start with an observational motivation, since we have many observers here in this awesome conference. MWC 758, as you see, right, you have this structures in the disk, and they look just like what you would expect from vortices. This image is amazing. That's from ALMA, but I'd like to highlight also that this has also been observed with VLA, so that you can do it in this overlay of ALMA and VLA, and have then a multi-wavelength view of this disk. So the millimeter strapping then millimeter size grains, that's what you're seeing here. With VLA, you're seeing bigger grains, and as you see, right, this extended structure here, when you look at VLA, becomes more compact. So this is an overlay of both of them. The bigger contour is the ALMA one, and the smaller one is the VLA. So this is exactly what we would expect from vortex trapping. This is a simulation here by Natalie Rettig, Hubert, and myself, where you see a vortex in the gas phase. And as you put grains of different Stokes number, as you decrease the Stokes number, the grain the concentration goes from very concentrated to more extended. Precisely what you see here with the ALMA, the smaller grains, and with the VLA, the bigger ones. All right. Now, we've been talking a lot about the vertical shear instability. Of course, there's a meeting about the vertical shear instability, but there are other ways to generate vortices in disks too. In the past decade of research in this field, we found also the convective overstability and the still controversial zombie vortex instability. But the thing is that they all operate in different regimes of cooling times, right? The vertical shear instability when the cooling time is very short, the zombie vortex when the cooling times are very long, and the convective overstability in between. You can convert these cooling times into opacities, right? And say, yeah, these three instabilities operated in very different regimes of opacity. And you can then map them into different regions of the disk, and this is what you get then when you do this mapping. In the inner regions of the disk and in the very outer regions where you have a lot of ionization, the MRI dominates. And yeah, in the very upper part, you're going to have the winds, but then in between, you're going to have the zombie vortex in the inner parts of the disk when the cooling time are longer. The disk is more adiabatic. The vertical shear instability dominates in the outer disk, where the disk is more isothermal, and then the convective overstability in between. What I like about them is that they all seem to saturate into vortices. Since we talked more about the VSI, let me just give a very brief intro to the convective overstability. Sorry, here. So what happens here is that if you have an entropy gradient, a negative entropy gradient in the disk, you see that if you can start from a non-vortical initial condition, and then the baroclinity will lead to vortices. The mechanism was elucidated here quite concisely by Henrik. You see, you can start from a blob, right, here in an equilibrium configuration. And if this blob here rises buoyantly, right, it will go to colder orbits. It will lose entropy as it goes into these colder orbits. So it will get denser. When it goes back to the equilibrium position, because it is denser, it's going to overshoot the equilibrium position. The amplitude of motion then will be higher. Now it's going to go further into hotter orbits. So then when it gets back to the equilibrium configuration, it's going to be hotter than what it was before, therefore more buoyant, and then it's going to overshoot it again, and the cycle continues in the linear growth, at least with no end until saturation kicks in, and then you build these big vortices at later times. So this is in a local model. I'd like to show here too. This is work in progress, doing global models of convective overhead instability. These are models done by Debanjan Sengupta, who is a postdoc here with us. You can see here that you can start right from the these linear modes, this convective modes, and then at later times you have these huge bulk motions in the box. We are still analyzing this. And as I said, what is interesting about them is that they all saturate into vortices, right? The VSI, the convective overhead instability also, and the ZVI. And vortices are very interesting for planet formation. So showing here some ancient results, I'm saying here, from classical antiquity back in 2008, a work that I did with Anders and Hubert. You see here in time, this is the gas phase and the pebbles. We had vortices here that in this case were done by the Rossby wave instability. You add the pebbles in this calculation, and then you see that the vortices trap them very, very, very fast. And then when you see the mass that is concentrated in these vortices, you end up with hundreds of objects of Moon mass and dozens of objects of Mars mass, right, and a few Earth mass objects. All that seemed quite good, except that, of course, these models were 2D and global. So there was this nagging feeling that we didn't have the resolution to be certain about these masses, right? So we've been then trying to fix that by running local models of Pebble trapping. So this is the same model that I showed before, but now here you also see what happens when you include the feedback, right, from the pebbles. For the low Stokes number, 0.01 and 0.05, statistically, they didn't change much. You still have trapping with pretty much the same concentration and extent, but as you go to higher Stokes number, you see that here the particles concentrated all in one point, and then here you have the back reaction starting to do something, right? And that led to the idea that maybe then you cannot concentrate pebbles too strongly in a vortex because they may disrupt them as the dust to gas ratio gets extremely high. This is what Natalie showed here. This is a model for dust to gas ratio 10 to the -2, and the model of dust to gas ratio 10 to the -4. As you see here in the 10 to the -4 model, the dust is being concentrated inside the vortex, and yeah, it does not disrupt the vertical structure. But in this case here, for higher dust to gas ratio 10 to the -2, it does. You look at the vorticity map, and you don't see the vortex anymore. Well, it turned out that we could show that this is something that only happens in 2D and is not going to happen in 3D. This is a model here without the dust feedback. So yeah, you see the dust here. So this is the dust, and this is the vorticity. The dust is being concentrated inside the vortices, yes. In the 2D, if you're only looking at the midplane, with the dust feedback, if you're only looking at the midplane, indeed, you don't see the vortex anymore. But it's pretty clear that in 3D, the vortex column continues above and below the midplane, and the trapping is still going on, right? So in 3D, trapping continues. This is what we're showing here too. Pebble trapping in 3D. So this is for the simulation 10 to the minus of dust gas ratio 10 to the -4. You can see here for the different dust to gas ratios, right, what the maximum dust to gas ratio achieved is. The 10 to the -4 is the green line, right? So even for this low metallicity, seeing that inside the vortex, you do reach dust to gas ratio of about 1, right? So the conditions probably would be there then for the streaming instability if we could resolve it, which we cannot in this model because of the resolution requirements. The next thing then is to introduce self-gravity in this simulation to find out what the masses of the objects that form in these vortices are. That's what we did here. It's also working in preparation. You're seeing here the vorticity and here the column density of pebbles. So after 2 orbits, after the insertion of the pebbles, 5 orbits and 12 orbits. And we see here, right, that the pebbles, they do get trapped inside the vortices. And then these white dots are the planetesimals, the form. So they form inside the vortex, as you expect. Soon they leave the vortex, and then new planetesimals form and inside them, and then it doesn't take long until you have planetesimals all over the place. Right. Now, if you look at the masses of them, turn out that they're not exactly planetesimals; they're protoplanets. So if you're looking here, so this is the mass function and the cumulative mass function of these objects. This is in units of the gravitational mass, more natural unit here in Earth mass. So you see here, as you go to different resolutions, which are the different colors, you're forming objects of less and less mass, but the mass of the most massive objects seems to be converging here between Earth and Mars mass, right? The slope of the cumulative mass function is about 1.6, which is also seen to be converged in the different resolutions, right? The burst of planet formation seems to be fast. This is what you see here. This is the dust density. So it reaches the Roche density, and less than 200 orbits, it stops, right? It's consuming most of the pebbles in the simulation, and then no more planetesimals are formed. The number then reaches, at least in this calculation, you see it reaches a plateau and then starts to decline and then reaches a new one here. This is the cumulative mass function in time. You see that after this burst here, which is about 150 orbits after the insertion of the particles, then it stops evolving, and it's constant after that time. And highlighting then what the differences are, right? This is the global 2D model. That's what we could do 14 years ago. And this is what you can do now with much more resolution in local 3D models. The masses are not that different, right? You still form Mars mass objects, Earth mass objects, just that we can do that now with more resolution. But the higher masses were still are the same. So indeed, we were converged at least the highest masses in those models. Increasing the resolution, we can reach lower masses, right? It would be great if you could go higher in this case too, like go to 1024. As you know, that takes a lot of computational time. But yeah, let's see, would be interesting to see how far how low in mass we can go here in these calculations. And so reach then my conclusions. The vertical shear instability and the convective overstability may be relevant for planet formation. The VSI occurs when you have a rapid cooling and a radial temperature gradient. The convective overstability when you have a finite cooling and a radial entropy gradient. They both saturate into vortices, and these vortices are very efficient pebble traps. You have a high particle load that disrupts the vertical motion around the midplane, but not the full column in 3D. The trapping properties of the vortex are retained, and the pebble load is high enough to lead to direct gravitational collapse. Right? The planet population is of planetary embryo mass. They are not planetesimals. You form objects among to Mars mass, and in the local models, they are resolved, right, in both gas and pebbles. The limitations of the models that I showed is that the resolution is so low enough that we don't resolve the streaming instability. It would be great to see how they coexist. And we don't model coagulation and fragmentation. So when the pebbles get into the vortex, the Stokes number will change, right, due to that. And since I still have some seconds, I'd like to give a shout out to the collaboration, right? There's awesome people across the US here that are working on this project. So with that, then, do I get a trophy for finishing on time? Right.
I'll think about that. Well, thank you, Brad, for the
for questions now.
So we have We have plenty of time for questions and comments, Vlad. So again, please raise your hand or type your question in the, let's see, Liz, do you want to go ahead?
Yeah, thank you, Vlad, for your talk. I was wondering if there is observation of gas in this MWC 758 disk, because as I remember, when Miriam Benisti in 2015 published the polarized scattered light of this disk, I don't think they observed vortex, but instead like spiral arms. Yes. And so I was wondering, like, what would you expect to, like, if we move on to the gas molecular line emission, would expect to see vortex or at this location where we think there's a pebble trapping?
Right. Thanks very much for the question. Indeed. So this is an overlay, including also the sphere observation. So that's not gas, but that's the small grains, right? That's infrared. And imagine that that's also tracing the gas, right? And indeed, that's something that I find very interesting because, as I mentioned also in the first day, this is clear evidence to me that the mid plane and the atmosphere are doing very different things, right? So you have that in the mid plane, the vortices, they are there, they are trapping dust, but the vortices do not continue all the way up to the atmosphere of the disk. That's what we are seeing here in some of the models, right? The VSI models that Thomas showed, you have a lid, right, where you decouple the gas and the dust. Therefore, the cooling time goes very, very high because the dust cannot cool. I mean, the gas cannot cool if it doesn't have dust, right? Increasing the cooling time, you shut down the VSI. So that's consistent with this picture here of MWC 758, that you get the vortices in the midplane, but in the infrared, you're not going to see them, right? Thomas showed that above about like 3 scale heights, you don't see them anymore, right? And even if that wasn't because of the gas decoupling, you start to have MHD effects in the upper layers of the disk too. And if that is the case, right, if you see this picture here, if you have MHD winds, they are also going to disrupt the vortex by magnetizing the flow,